I want to tell you about something that kept me awake for weeks when I was a young man. You see, everyone asks the same question eventually. Why can't we just go faster? Build a bigger engine, burn more fuel, keep accelerating until we reach the speed of light and beyond. Most people think it's just an engineering problem. Give us enough time, enough technology, and we'll crack it. Honestly, I thought that too when I was 17 years old, lying on my bed in Far Rockaway, staring at the ceiling. But then I discovered something that Einstein had hidden in plain sight. Something so strange, so deeply counterintuitive, that even after I understood the mathematics, my gut refused to believe it for years. Let me take you on the journey that shattered everything I thought I knew about speed, about space, and about time itself. Now, let me start by telling you where my head was at before I really understood this thing. I grew up tinkering with radios in my basement, taking things apart, putting them back together. I had this beautiful, mechanical view of the universe. You push something, it moves. You push it harder, it moves faster. Simple. Obvious. When I was about 15, I started reading about Einstein. Not the mathematics yet, just the ideas. And everyone kept saying the same thing: nothing can go faster than light. 300,000 kilometers per second. That's the limit. Period. And I remember thinking, why? What's so special about that particular speed? It seemed completely arbitrary to me, like someone had just picked a number out of a hat and declared it the universal speed limit. I couldn't accept that. Nature doesn't work that way. Nature doesn't have arbitrary rules posted on cosmic signposts. So I started digging, and the first thing I learned was that this wasn't just Einstein's opinion. He had derived it. He had started with two simple assumptions and followed the logic wherever it led. And where it led was absolutely crazy. Let me tell you what those assumptions were, because this is where everything starts. First assumption: the laws of physics are the same for everyone moving at constant speed. Sounds reasonable, right? If you're in a smoothly moving train with the blinds closed, you can't do any experiment that tells you whether you're moving or sitting still. The physics works the same either way. Second assumption: the speed of light is the same for everyone. Now this is the strange one. This is where my intuition started screaming at me. Think about what this means. Let's say I'm standing still and I shine a flashlight. The light zooms away from me at 300,000 kilometers per second. Fine. Now let's say you're in a spaceship moving toward me at half the speed of light, and you measure that same beam of light as it passes you. Common sense says you should see the light moving at as 1.5 times its normal speed, right? Like if you're running toward a thrown baseball, it approaches you faster than if you were standing still. But that's not what happens. You measure the light moving at exactly the same speed I measured it, 300,000 kilometers per second. Not faster, not slower. The same. I remember reading this for the first time and thinking there must be a typo in the book. I read it again. I read 3 other books. They all said the same thing, and they all had experimental evidence to back it up. This was experimentally verified before Einstein even published his theory. Michelson and Morley had done the experiments in 1887. They were trying to detect the wind, the effect of Earth moving through space on the speed of light. They expected to find it. They found nothing. The speed of light was stubbornly, mysteriously constant. And here's what Einstein did that nobody else had the courage to do. He said, okay, if that's what the experiments show, let's take it seriously. Let's assume the speed of light really is constant for all observers and see what happens. What happened was that space and time fell apart, or rather, they came together in a way nobody had imagined before. Now let me tell you where this gets really interesting. When I was at MIT as an undergraduate, I finally sat down with the actual mathematics of special relativity. Not the popular descriptions, not the thought experiments. the actual equations, and I discovered something that the popular books never quite explain properly. You see, everyone focuses on what can't happen. You can't reach the speed of light. You can't go faster than light. Can't, can't, can't. But nobody was explaining why in a way that made physical sense to me. So I started thinking about it my own way. Let me share with you the thought experiment that finally made this click for me. Imagine you're in a spaceship and you have a perfect engine that can provide constant thrust forever. You start from rest and you begin accelerating. 1 g of acceleration, the same as Earth's gravity. Comfortable. You could live like that. In Newtonian physics, your speed would just keep increasing linearly. After 1 year of accelerating at 1 g, you'd be going about 300 million meters per second. You'd have already exceeded the speed of light. But that's not what happens. In Einstein's universe, something very different occurs. And this is where I had to let go of everything I thought I understood about velocity. You see, velocity isn't what we think it is. We think of it as simply distance divided by time. But whose distance? Whose time? When you're moving at significant fractions of the speed of light, your measurements of distance and time are as different from mine. Let me put it this way. From your perspective inside that accelerating spaceship, you're definitely speeding up. You feel the acceleration, your speedometer, if you had one that measured your velocity relative to your starting point, would keep climbing. But here's the strange part. As your speed increases, time itself begins to slow down for you relative to someone watching from outside, and distances in the direction you're traveling begin to contract. I remember working through these equations late one night in my dormitory room, and suddenly I saw it. The reason you can never reach the speed of light isn't because some force stops you. It's because the definitions of space and time themselves change in a way that makes the speed of light unreachable. It's like, you know that dream where you're running towards something, but the hallway keeps stretching. It's a little like that. But it's not a dream. It's the actual structure of reality. Now, I need to introduce you to a concept that Einstein gave us, and it's the key to understanding everything that follows. The concept is spacetime. Before Einstein, we thought of space and time as time, two separate things. Space was the stage where events happened, and time was the universal clock ticking in the background. Einstein showed us that this is wrong. Space and time are woven together into a single fabric, space-time. And when you move through space, you're actually trading your motion through time for motion through space. Let me explain what I mean by that, because this is crucial. Right now, sitting wherever you are, you're not moving through space. But you are moving through time at the rate of 1 second per second. Your entire velocity is pointed in the time direction. Now, when you start moving through space, something remarkable happens. Your velocity through space-time, which is always constant, always equal to the speed of light, begins to tilt. Some of your motion through time gets redirected into motion through space. And here's the kicker: the faster you move through space, the slower you move through time, not because of some mechanical effect, but because your direction in space-time has changed. This is why clocks on fast-moving objects tick slower. This is why time passes differently for astronauts on the International Space Station. They're moving through space, which means they're moving through time more slowly. When I first truly grasped this, I sat back in my chair and just stared at the wall for about 10 minutes. The universe was so much stranger and more beautiful than I had imagined. But then something unexpected happened. I realized I still didn't understand the real reason we can't reach light speed. You see, everything I just told you explains why time slows down and space contracts as you go faster. But it doesn't quite explain why there's this absolute barrier at light speed. It doesn't explain why you can't just push a little bit more and cross over. So I kept digging. And what I found next is something that I don't think most people truly appreciate, even those who think they understand relativity. Let me ask you something. When you push an object to accelerate it, what are you actually doing? You're adding energy to it, right? Kinetic energy, the energy of motion. In Newton's physics, the relationship between energy and speed is simple. Kinetic energy equals 1/2 times mass times velocity squared. Double your speed, quadruple your energy. Triple your speed, 9 times the energy. But there's no limit. You can keep adding energy and keep going faster forever. Einstein showed us that this formula is wrong. Well, not wrong exactly. It's a very good approximation at low speeds. But at high speeds, something very different happens. The real formula for the total energy of a moving object is E equals gamma times mc squared, where gamma is the Lorentz factor. Now, don't worry about the mathematics too much. What matters is what this formula does. At low speeds, gamma is very close to 1, and the formula reduces to Einstein's famous E equals mc squared, plus the familiar kinetic energy term. So far, so good. But as you approach the speed of light, gamma doesn't just increase, it increases without limit. It goes to infinity as your speed approaches the speed of light. And this is where I finally saw what was really going on. The energy required to accelerate an object increases more and more rapidly as you approach light speed. Not linearly, not quadratically, but hyperbolically, shooting up toward infinity. To accelerate a mass, any mass, even a single electron, to exactly the speed of light would require infinite energy. Not just a lot of energy, not just more energy than exists in the universe. Infinite energy, an amount that cannot exist. Now, when I was at Los Alamos during the war, working on the atomic bomb, I had a conversation about this with one of the other physicists. I don't remember who might have been Beth, might have been Weisskopf. But I remember saying something like, so the speed of light isn't really a speed limit. It's more like a Désir asymptote. You can get closer and closer, but you can never actually reach it. And whoever I was talking to said, yes, but that's not the interesting part. I asked what he meant, and he said, the interesting part is why the universe is built this way. And that question haunted me. Because up until then, I had been focused on what the equation said, not why they said it. And the more I thought about it, the more I realized that the speed of light, being a limit, wasn't just some arbitrary feature of our universe. It was deeply connected to the very possibility of cause and effect. Let me tell you what I mean. In spacetime diagrams, we draw something called a light cone. From any event, any point in space and time, you can draw all the paths that light could take, both into the future and coming from the past. This creates a cone shape. Everything inside your future light cone is something you could potentially influence. Everything inside your past light cone is something that potentially have influenced you. But here's the crucial thing. Events outside your light cone are causally disconnected from you. They cannot affect you, and you cannot affect them, not because of any practical limitation, but because of the fundamental structure of spacetime. Now, what would happen if something could travel faster than light? It could get outside its own light cone. And here's where it gets really strange. I remember working this through and feeling a chill go down my spine. If something could travel faster than light, then there would exist reference frames where that thing arrived before it left. Let me say that again because it's so important. Faster than light travel doesn't just mean going really fast. It means time travel. It means effects preceding causes. It means the entire logical structure of the universe breaking down. Einstein understood this. He knew that the speed of light wasn't just a speed, it was the boundary between cause and effect. It was the speed of causality, the fastest that any influence can propagate through the universe. And suddenly, what had seemed like an arbitrary cosmic speed limit became something much more profound. The speed of light is the speed at which reality is sewn together. Now, this is where my understanding completely shifted, because once I saw the speed of light as the speed of causality, I started asking a different question. Not, why can't we go faster than light? But why is the speed of causality what it is? And I'll be honest with you, I don't think we have a complete answer to that question even today. But I can tell you what I think, based on decades of thinking about these things. The speed of light isn't really about a light. I think that's one of the great confusions that people have. They think there's something special about light that makes it go at that speed. It's the other way around. There's something special about that speed, the speed of causality, the cosmic speed limit, and light just happens to travel at that speed because light has no mass. Anything with no mass must travel at the cosmic speed limit. It has no choice. And anything with mass cannot reach it. The universe is divided into two categories: massless things traveling at exactly c, and massive things forever trapped below it. During my time at Caltech, I used to explain it to my students like this. Imagine you're walking through a thick forest. The density of the trees represents the Higgs field, this quantum field that permeates all of space. Now, some particles, like photons, are small enough to slip between the trees without touching any of them. They can move freely at the maximum possible speed, but other particles, like electrons and quarks, are bigger. They keep bumping into trees, getting slowed down, accumulating what we call mass. They can never move as freely as the photons. Now, I should be careful here. This is an analogy, and like all analogies, it breaks down if you push it too hard. The Higgs field doesn't literally slow things down, like friction. What it does is give particles inertia, resistance to acceleration. But the basic idea is right. Mass is what separates the particles that can reach light speed from those that can't. But here's what I noticed that no one else seemed to be talking about. And this still amazes me. The cosmic speed limit, what we call the speed of light, isn't just about particles moving through space. It's about everything. Every force, every interaction, every way that one part of the universe can influence another. They all respect this limit. Gravity travels at the speed of light. When the sun moves, the change in its gravitational field propagates outward at exactly c, not faster. Electromagnetic forces travel at the speed of light. When you jiggle an electron here, the effect on electrons far away travels at exactly c. Even the nuclear forces, as far as we can tell, respect this limit in the sense that no information can travel faster than light. The universe is locally connected. Every point in space can only talk to its immediate neighbors, and the fastest these neighbors can pass along a message is at the speed of light. It's like, imagine a vast ocean of information, and the fastest any ripple can travel is c. And I remember having a profound realization about this, sitting on the beach in Brazil during my sabbatical there. The speed of light isn't just about speed. It's about the bandwidth of reality. It's the rate at which the universe can update itself, the maximum frequency at which existence can process information. When you think about it this way, the question, why can't we go faster than light, transforms into, why would we expect that we could? We are made of processes that operate at or below this limit. Our very thoughts, the electrical signals in our brains, propagate far below light speed. We are creatures embedded in a reality that has a maximum refresh rate, and asking to exceed that is like a video game character asking to jump out of the screen. But I wasn't satisfied with this. I kept pushing because I wanted to know, is there anything in physics that might allow us to get around this limit? Not by going faster than light, but by taking shortcuts. Now here's what changed everything for me about this question. Because it turns out there might be loopholes, and they're hidden in Einstein's own theory, not special relativity, but general relativity. You see, everything I've told you so far is from special relativity. which deals with flat spacetime, space that isn't curved by gravity. But our universe isn't flat. Mass and energy curve spacetime, and in curved spacetime, things get much more interesting. I remember when I was first learning general relativity. This was in graduate school at Princeton. I was working with John Wheeler, who was one of the great relativists. And Wheeler had this way of looking at things that opened my eyes. He used to say that spacetime tells matter how to move, and matter tells spacetime how to curve. It's this beautiful dance. And once I understood that dance, I started to see possibilities I hadn't considered before. You see, special relativity says you can't travel through space faster than light. But what if you could take a F shortcut through spacetime itself? Wheeler introduced me to the concept of wormholes, theoretical tunnels through spacetime that could connect distant regions. If a wormhole existed, you could step in one end and step out the other, having traveled what appears to be a vast distance almost instantaneously. Now, let me be very careful here, because I don't want to mislead you. As far as we know, traversable wormholes probably don't exist in our universe. The equations allow for them mathematically, but to actually create one or keep one open would require exotic matter with negative energy density, stuff we've never seen and might not be possible. But the mere fact that the equation's eyes allow for shortcuts is philosophically important. It means the cosmic speed limit is more subtle than it first appears. There's another concept that emerged later, called the Alcubierre drive, named after Miguel Alcubierre, who proposed it in 1994, long after my time thinking about these things, but built on foundations I understood. The idea is that instead of moving through space faster than light, you could contract space in front of you and expand it behind you. The spaceship itself never locally exceeds light speed, but the warping of space around it could effectively move you faster than a beam of light traveling through normal space. Again, this almost certainly can't work in practice. It would require astronomical amounts of negative energy. But it shows that the speed limit isn't quite as simple as nothing can go faster than light. It's more like nothing can locally outrun a light signal in its immediate vicinity. Now, I want to tell you about something that does appear to violate the speed limit, because it confused me for years until I truly understood it. Quantum entanglement. I spent a lot of time thinking about quantum mechanics, as you probably know. And there's this phenomenon where two particles can be entangled, connected in such a way that measuring one instantly affects what you'll measure on the other, no matter how far apart they are. Einstein called this spooky action at a distance. He didn't like it. He thought it showed something was wrong with quantum mechanics. But experiments have confirmed it again and again. You can have two particles light years apart, and when you measure one, the state of the other is as instantly correlated. Faster than any light signal could travel between them. So have we found a loophole? Can we use entanglement to send information faster than light? The answer is no, and this took me a long time to truly understand. The quantum correlations are real, but they cannot be used to transmit information. The randomness of the measurement screens the correlation in such a way that no usable signal can be extracted. It's as if the universe has a rule: correlations are allowed, but communication must always obey the speed limit. Nature protects causality even when doing things that seem to violate it. I find this beautiful. The universe isn't just obeying a speed limit, it's actively protecting the structure of cause and effect, even in its strangest phenomena. And then it hit me. After years of thinking about this, after equations and thought experiments and conversations with the greatest minds I knew, the speed of light isn't a barrier that the universe put up to frustrate us. It's not a wall we might someday break through with better technology. It's not even really about light. The speed of light is the speed of existence itself, Let me explain what I mean, because this is the heart of it. Every event in the universe, every interaction between particles, every change from one moment to the next is connected to other events through spacetime, and the speed of light is the rate at which these connections can propagate. If you could somehow go faster than light, you wouldn't just be traveling quickly. You would be disconnecting yourself from the causal structure of the universe. You would be somewhere that isn't connected to where you were by any chain of cause and effect. And that's not just impossible, it's meaningless. It's like asking what's north of the North Pole. The question contains a misunderstanding of what North S means. Einstein saw this. He saw that space and time aren't the backdrop against which physics happens, they are physics. The geometry of space-time is the physics, and the speed of light is the conversion factor between space and time, the fundamental constant that tells you how space-time is structured. In a very real sense, asking, why can't we go faster than light, is like asking, why is 1 meter 1 meter? Or, why is 1 second 1 second? The speed of light defines our units. It defines what distance and duration as mean in relation to each other. In fact, we now define the meter in terms of the speed of light. It's the distance light travels in 3299, 792, 458 of a second. The speed of light is no longer a measured quantity, it's an exact, defined number. This is humanity's recognition that c is more fundamental than our units. And here's what moves me most about this, what makes me feel the deepest sense of wonder. The universe didn't have to be this way. There's no logical necessity that says causality must be local, that information must have a finite speed. We could imagine universes where everything happens instantaneously, where every particle knows about every other particle right now. But we don't live in that universe. We live in a universe where events are locally connected, where causality spreads outward at a finite speed, where there are things we cannot yet see because their light hasn't reached us yet. And this locality is what makes everything interesting. It's what allows for complexity. It's what allows for us. If the universe were non-local, if everything could influence everything else instantly, there would be no room for isolated systems, no room for things to develop on their own, no room for evolution, for life, for minds contemplating the cosmos. The cosmic speed limit isn't a limitation, it's a gift. It's what gives the universe room to be interesting. This changed how I see reality. When I was young, I wanted to overcome the speed of light. I saw it as a challenge, a barrier to be broken. I dreamed of starships traveling to distant galaxies in the blink of an eye. Now, I wouldn't change it for anything, because I understand that the speed of light isn't something imposed on the universe from outside. It is the universe. It's the heartbeat of existence, the fundamental rhythm at which reality processes itself. People sometimes ask me if I'm disappointed that we'll never travel to the stars the way science fiction imagines. And I tell them, look at what we have instead. We have a universe where light takes 4 years to reach us from the nearest star. 4 years! That means when we look at Alpha Centauri, we're seeing it as it was 4 years ago. We're time traveling every time we look up. When we look at the Andromeda Galaxy, we're seeing light that left 5 million years ago, before humans existed. The most distant galaxies we can see, their light has been traveling for over 13 billion years, almost the entire age of the universe. The night sky is a time machine. And it only works because light has a finite speed. I hope you can see what I see now. The speed of light isn't a prison wall keeping us trapped. It's the structure that makes the universe our universe. A vast, evolving, causally connected whole where the past genuinely shapes the future, where events have consequences, where stories can unfold. This is the beauty of physics. It takes something that seems like a limitation and reveals it to be the very thing that makes existence possible. Einstein didn't just discover a speed limit. He discovered that speed and limit aren't quite the right words. He discovered that space and time are woven together in a way that defines what fast and slow can even mean. And that discovery, that hidden truth that he put right there in his equations for anyone to see, that's what shatters the everyday mind and rebuilds it with a deeper understanding of what reality is. I've spent my whole life trying to understand how nature works, and after all these years, I've come to believe that the deepest truths are always like this. They seem like limitations at first, until you realize they're the very things that make everything else possible. The speed of light, the speed of causality, the speed of existence. What a universe we live in! This is the beauty of physics, and I wanted you to experience it with me.